And since this is going to be something that's on the test, so I covered some essentials of that last time, and that means I can just go ahead with an example. So this would be, what I'm going to do now, a perfect example of the kind of problem you see on a test, besides the practice problem that you have. Whoops. Oh, 1, 2, 3, 4. So that makes me 4/7 of a Jedi. Okay. If you don't get that, just smile and nod. Okay. Now, all right. And this is section 1.8 of the notes. Okay. So here's our function that we're going to work with. Okay. All right. So the problem is, this is the sort of thing that you'd be asked to do on a test. Find any local maxima, minima, and we have something new. I mean, you have local maximum in single variable case in calculus 1, but in multivariable you can also have saddle points, where you have it behaves like a local minimum in certain directions, but a local maximum in others, giving a graph of the appearance of a saddle. Now, functions may not necessarily have all of these things, but whatever's there, the problem is to find it. Okay. So just as when you were finding maximum min in calculus 1, you took the derivative, set it equal to 0. It's a similar idea. So the first thing you do is find where the gradient of f, which is a vector consisting of partial f with respect to x, partial f with respect to y, is equal to the 0 vector. So you're finding your critical points where both partial derivatives, or all partial derivatives, however many you have, in this case 2, are equal to 0. So what is the derivative of this with respect to x? Yeah. Okay, so this must be equal to 0. And then the derivative with respect to y?
4y plus 16 minus 3.
Yeah. Okay.
Wait, would it be 4x?
Yes, for x. Okay. All right. Now, both derivatives had to be 0 simultaneously. So whereas before in calculus 1 you just had one equation to solve, and usually you could do some straightforward algebraic manipulations, here you have a system of equations that must be satisfied. Now, in this case, because the function itself was quadratic in terms of x and y, of course your derivatives are going to have degree 1 less than that. So we end up with a system of linear equations. So if I write it this way, 12x plus 4y is equal to 1, 4x plus 16y is equal to 3. So this is the sort of thing you've had to do, well, it certainly comes up in linear algebra class, but also lower level math to solve systems of a small number of linear equations. How do you go about solving for solving this kind of system? You definitely would have done it before.
You can either like multiply one of them by a number and do the whole subtract the out thing, or you can do a matrix or
yeah, basically, however you look at it, whether it's a matrix perspective or not, it's elimination and substitution. So I'll show one approach that you can use involving elimination and substitution, I can take this equation and actually, I'm going to use the other one. I can take the second equation and solve for x in terms of y. So I can, if I rearrange this and isolate x, what would I get from the second equation? Yeah, I'll leave it as a fraction. 3 minus 16y over 4. Yeah. Okay. Now, what can I do with that?
Substitute in, right?
Yeah. Now substitute that into the other equation. So that way we can. So this is what I mean by elimination. We're eliminating x to get one equation and only y. So, so now we're going to get 12 times all that, and yes, I meant the numbers were contrived to work out nicely in terms of getting rid of this pesky fraction. So now you're going to have 9 minus 48y plus 4y is equal to 1. So now you can go ahead and rearrange this and to solve for y. And what are you going to get when you do that? Okay, I just gave away as a fraction, but
Negative, positive 2 left.
yeah, so you get 8 over 44, which reduces to 2 over 11. Just because you can rearrange this, you get minus 44. By combining like terms, you get that. And then solve for y. Okay. Bless you. And in this review of algebra, what do I do with that to finish this off?
You put it back into the...
Put it back into the equation I have for x. I already have a formula for x in terms of y, but now I have y. So I can substitute into here, and I get x is equal to 3 minus 16 times 2 over 11, all over 4, and that will simplify to 1 over 44. So this system of linear equations, as most but not all systems do, has a unique solution. So we have one critical point. So x is 144, and y is 844, or 2 over 11. Okay. Now this example had just one, but in general you may have more than one. It just depends on the function involved. So any questions about getting the critical point? Right, so once you have your partial derivative, instead of equals 0, it's just an algebraic exercise of one kind or another to get what critical points you have. As a side note, something to keep in mind for tests. It's very common practice, unfortunately, in many classes for students to assume that for whatever test problem, the numbers work out nicely. And if they don't, then you must have done something wrong. That assumption is not valid in my classes. Sometimes it happens, sometimes it doesn't. Just do the problem right. Focus on that. Don't make those kind of assumptions, because those are games not worth playing. Okay. Now that we have a critical point, we don't know what kind of feature this critical point is in the graph of the surface. Is it a local maximum, minimum, or a saddle point? So for that, we have to use the multivariable version of the second derivative test. And I briefly showed you that last time, but now you can see it in action, if you will. Oops. Okay. Well, okay. So. All right, so what we need, called the Hessian of f, which is just a fancy way of saying it. We need all the second partial derivatives. Now, fxy and fyx are the same, so we don't need to get those once. So, but we're going to have them all in one place. So, going back to a previous board, we have our first partial derivatives written down. So, so what would fxx be?
12.
Yeah, because we just have 12x, and just so you can have it on the same board, in case anybody's watching this video, I'll just repeat what the first partial derivatives were. Okay, is 12. Okay, and then fyy, 16, and then fxy,
4.
is 4. And then this would also be 4. Okay. So then what we do is, so once you have those second partial derivatives, in this case they happen to be constants. If they were not constants, what you have to do is plug in the critical points. Okay. And you're going to test each one separately, because you only care about these second derivatives at those critical points. So once you have, so ultimately you have numbers for your second partial derivative. So now you can do this quantity. I call it D because it's really a determinant of its matrix. It's fxx, fyy, so the ones that have the same variables repeated, minus the mixed partial derivative squared. And so that's going to be 12 times 16 minus 4 squared, so we get 176. Okay. Now, just to recap from last time, what do you do with that? So, if D is positive, and then your partial derivatives of the same variables, xx and yy, are also positive, that is a min. If D is again positive, but these partial derivatives are negative, that is a max. If D itself is negative, you can stop right there and say it is a saddle point. And if D equals 0, then you know nothing. It's inconclusive. So our one and only critical point is what? It's going to be a local minimum. Okay? So because these diagonal entries, fxx and fyy, are positive, then the point 144, 2 over 11 is a local minimum. Okay. And that's it. That's the end. So the idea is we find whatever critical points there are, and then we classify them as max, min, or saddle point.
So if you have more than one critical point, you have to do that twice.
Yes.
However
many times you have. Yeah. Okay. All right, so questions about this one?
On the test, there's most likely only going to be one of these, like as far as having to find one local minima or maxima, because this is a sort of a lengthy problem, it seems like.
Yes, it can be. And the thing is, okay, there are going to be 6 prompts on this test. This one would would be one of the lengthier ones, whereas yes, even though the problems will be worth similar number of points, the amount of time spent is going to be varying. Like for instance, you have certain problems that are going to be relatively quick, like one where you just compute partial derivatives, or one where you compute directional derivative. Yes, so you definitely want to keep that in mind as far as pacing goes. That so it is expected that of the 50 minutes that you'll have, this one problem will get a disproportionate share. But what I would suggest is maybe work out, if you go out of order if need be, and work out some of the ones that might be quicker. Get those in the bag, and then you're not working on this one in a freaked out state. Yes.
So this would be a max. 1 over 44 and 2 over 11 will have to be negative.
Not the v second partial derivatives, fxx, fyy. Those would be
12 and
negative.
16.
Yeah.
Yes, it-
Yeah. So these entries.
That's right.
And D, the equation for D is just straight out of the book, correct?
Yes.
Okay.
It happens to be, but this is why we write it second partial derivative this way. It's the determinant of this 2x2 matrix. So if you remember that from other classes, that's what it is. But
When you say fxx and fyy would have to be negative, do you mean each individually has to be negative, or multiplied together has to be negative?
well, it turns out that when D is positive, really, actually, I think, they're both going to be the same sign no matter what. So really checking one would be enough. Okay. Any other questions?
You could just about find out if there's a local min or max just from the start, practically taking the second derivative.
Depends on the function, because in this case it works out pretty nicely because the function itself is quadratic. Therefore, the second derivatives are all going to be constants. So
You didn't have to input none of them.
so that's something that's very function dependent. Because I've given problems where there's a few critical points that all end up with different classifications. Okay. You have a question?
So for this point over here, when you're finding x and y, would it possibly be faster if you went ahead and found what x and y would put the first term to 0 and have all the possibilities right there, and you know that one of those possibilities would have to fit into the next equation equals 0?
Well, yeah, it is a good idea to break it down like that. Like, for instance, if you look at fx, assume that's what you're saying, that you find where fx could be 0.
Right.
And then you'll examine, say if you get multiple possibilities, now you plug each of those in turn into fy and see what also makes that 0. Yes, it is a good idea to do it like iteratively like that. Like where, and again, it's something that's function dependent. Here, like, okay, it's a linear system, you know how to do that. But for more general functions, yes, I would recommend that. And I will say for purposes of a test, if a function has multiple critical points, of course, for full credit, the idea is to find all of them and classify them properly. But again, I do give partial credits, and if you show me that you understand the process of, find a critical point and go through this process of classifying as maximum and saddle point, but that's worth a lot of credit. I'm more in terms of assigning partial credit. I'm more concerned about seeing your knowledge of uniquely Cal 4 concepts than other things like from previous classes. So the more Cal 4 knowledge you show, the more partial credit you'll get. So if you mess up algebraically and don't get all the critical points because of that, are you going to lose some points? Yes, but showing me that you understand this that's part of this course will still help you a lot. So, and with each problem being worth 16 points, that gives me a fair amount of leeway when it comes to giving partial credit. So, just do your best not to leave anything blank, because then you kind of hamstring me at that point. I have to give you a 0 on that problem. So, so I want to give credit. So give me something to go on.
I have a question.
Yeah. Yes.
For your equations, for quadratics, are you always going to have just one critical point? Or how does that work?
Almost always, because when it's quadratic, you will always have a linear system. But a linear system usually has a unique solution, but it may have none or infinitely many in these isolated cases. So, yeah, so it's almost always the case. I'm not going to give a function that's infinitely many critical points. I mean, I'm not likely to give one that would have none either, because it's not very interesting. It cuts out this whole part of a problem. So, in fact, no, I'm not going to do that. So,
If it was a cubic function, would it have 2 or?
that's when then you're getting into systems of nonlinear equations, and it's very difficult to make any general statements about that. Because now the thing is, which is a contrast to calculus 1, because in that case, your derivative would be a quadratic function. You do quadratic formula, you get 2 roots. So then it really is clear cut. But when you have x and y involved together, I can't say anything for sure. You have a question? Yeah. All right. So now, another kind of problem related to max and min is also a generalization of a problem you have to solve in calculus 1, where you would be given a function and an interval, and you had to find a max and absolute max and min on that interval. So you had to find critical points in the interval, and you had to remember, this is where most people mess up, if they messed up, checking the endpoints. Similar situation in multivariables. And I think the best thing to do in this case is also to step through an example. So, finding absolute max min on some sort of bounded domain. So in other words, we're not looking at all of R2, the whole space. We're just looking at a certain portion of it. Okay, so as an example, here's our function. And the problem is to find the absolute max and min of this function on a triangle with these vertices 0, 4, 0, 0, 4, 0, and 0, 3. So go ahead and draw that triangle. 0, 0, 4, 0, 0, 3. Okay. So one thing that makes this problem a lot more complicated than in the single variable case, in single variable you're given an interval and you had 2 endpoints, 2 x values. So that was easy. You just plug in those x values into your function and see what you get. Here, the boundary is not just a couple of points or even these 3 vertices. It's this whole line segment, this whole line segment, this whole line segment. All of those together make up the boundary of this triangle. So you have to check for those whole segments for possible absolute max or min. Okay. So your candidates for an absolute max or min, you have critical points, but only critical points that are inside the domain. If you find any that are outside, you ignore them. And then the other possibility are any boundary points. Okay. So we're just going to gather these candidates one at a time and see what we get. Okay. So the first part of the problem is similar to before. We have to find the critical points. So from our function, what is fx?
2x minus 4
Yeah. And then fy?
is 6y minus 6.
Yeah. And you set both of these equal to 0. This is actually easier to handle than the last exercise. So what's our critical point going to be?
X equals 2 and y equals 1.
Yeah, so you can just go ahead and solve these. This has worked out nicely that the first equation is dependent only on x, the second equation is dependent only on y. So you can solve them independently. And that is your one and only critical point. And if you check, if I were to plot that point here, x is 2, y is 1, it is in fact inside the triangle. So it is as a candidate for an absolute max and min. So what I'm going to do over here, I'm going to make a list of candidates of points that could be maxes or mins. So this is the first one. Because once we have all of our candidates, we're going to plug those points into the function and see what values we get. Smallest one's the absolute minimum, largest one's the absolute maximum. But now we have to find out what other candidates we have. So now that we're through with critical points, we have to check each edge of our triangle. So the way to do that is to get an equation that describes each edge. And we're going to consider the three edges separately. So first we have the bottom edge, this one right here. So it includes the points 0, 0, and 4, 0. So if you think in terms of equation of a line, what's the equation of that line that defines this bottom edge?
Y equals 0.
Y equals 0. So all you have to do is now you can take that and plug that into the function. But it's not the entire line y equals 0. It's just the portion that's the base of that triangle. So we need to restrict x. What are values of x to consider?
It's greater than or
Between
equal
0 and 4.
Yeah, between 0 and 4. So this equation and this set of inequalities describes the base of this triangle. So that's one edge. Now, what about the left edge? So we want to describe that in a similar fashion.
Y equals 3.
Not equal 3, but. So this edge right here,
X equals 0.
x equals 0, and we need to restrict y.
So y is between 0 and 3.
Yeah, y is between 0 and 3. Okay, so we would plug x equals 0 into a function and only consider y value between 0 and 3. And we'll do that in a moment. But we have one more, the top edge, this right here. Now, it's neither a horizontal nor vertical line, but what we could do is describe it as like y equals mx plus b form. Well, what is the slope of that line going to be?
3 over 4.
Well, not 3/4, but negative.
Negative. Okay, sorry.
Yeah. So x, and then the y-intercept, which is 3. Okay, and then what we can do is we can restrict x between what and what? 0 and 4. So now we have full descriptions of all 3 pieces of our boundary, however many pieces you have. So now we can check each of these to find out if there are any of our points that are a candidate for an absolute max or min. Okay, now for the bottom edge, we're looking at the function f where x 0, because we're setting y equals 0, and then the function reduces to just x squared minus 4x, and we're only considering x between 0 and 4. So now what we're doing is we're solving a one-dimensional absolute max, absolute min problem, just like you did in Calculus 1. It's no different. You give it a function and an interval, so we find the absolute max and min along that. So I'm going to call this g of x. So now you can do what you did in Calculus 1. Take a derivative, set it equal to 0. So what is g prime of x?
2x minus 4.
2x minus 4. So, and you set that equal to 0. So we get, for a critical point,
X equal to 2.
x equal to 2. Now, x equal to 2 is not a critical point of the original function f of xy, but it is a critical point along this edge. So, so this is a candidate, and these guys, the endpoints, those are also candidates. So if I add to my candidate list, I have 0, 0, because that's from the left endpoint, 4, 0, because that's the right endpoint, and then 2, 0, that's the critical point. So the absolute max or min could occur at any one of those points. Now, I said earlier we have to plug in all of our candidates into the function f of xy, but here these are along this edge. So in fact, this one is particularly convenient. We can just use this when we're on this edge. So we can plug in x equals 0, 2, and 4 right now, using this instead of going back to f of xy. So if I plug in these, like I'm going to get 0 from this one, and I'm also going to get, if I plug in x equals 4, I'm also going to get 0. And if I plug in x equals 2, I'm going to get minus 4.
And you're plugging that back into this equation, or?
Yeah, which is equivalent to if I plugged in these points with y equals 0 into the original. So it's just more convenient if we use this when we're dealing with this edge. Okay. All right. So, all right. So that gave us some candidates for absolute max and min. But now we do the same thing with the left edge. We look at the function f x y, where now x is 0, and y remains a variable, and we get 3y squared minus 6y, and y is between 0 and 3. So this is a candidate, this is a candidate, except this one, x and y are both 0. We've already considered that, so we don't need to look at it again. And we can find, I'll call this h of y. So our derivative is 6y minus 6, so I get y equal 1. So now we have 3 candidates from this edge, we have 0, 0, but we already have that one. We have x is 0, y is 3, because that's an endpoint. And I also have x is 0, y is equal to 1. And I can plug all of those points, so y is equal to y is equal to 1, y is equal to 3 in here. So if I plug in y equals 1, I get minus 3. And if I plug in y equals 3 into this condensed version of a function, I get
You get 9.
27 minus
9.
9. Okay. So right now, this point is looking like will very well be the absolute max. Okay. So any questions about this edge?
Where'd the negative 4 come from?
When I plugged in x equal 2, this critical point in here.
Okay, yeah, I got you.
Okay. All right. Now there's one more edge. This one's a bit of a pain. So the top edge, we have f of x, and then our y value, we have the equation of that line there. So that's minus 3/4 x plus 3. So this is your y. You're substituting that in whenever you see y. And that's kind of a pain to work out. Don't worry, there isn't this kind of problem on the test. So what happens is when you make that substitution for y into our original formula, what you get is 43 over 16 x squared minus 13x plus 9. So now you have to, I'm going to call this, I'm running out of letters, s of x. So this is what f of xy looks like along this top edge. So now I do the same thing. X is between 0 and 4, but here we don't need to look at the endpoints because those vertices, we've already looked at them. We've already plugged those into f. All we need, last candidate is any critical point from here. So s prime is, what? 43 over 8x minus 13. And we set that equal to 0, and that gives us one critical point, which turns out to be 104 over 43. And if you check, that critical point actually is along the edge. So it is something to include. And that's our last candidate. X is 104 over 43, and y is equal to, if you just plug that back into the equation for a line, you get 51 over 43. So these are our 7 candidates. So all that's left is to plug in these last 2 values into your original function f of xy. And what you would get is minus 7 in this case, and this one it's minus 289 over 43. So now you can see whichever one is the largest is the absolute max, whichever one is the smallest is the absolute min. So it turns out this one is the absolute max, and this one is the absolute min, because this is pretty negative, but it's not quite as negative as minus 7. This falls short. So this is what you're doing, is you're looking for any critical points in the interior of your domain, and then on every piece of a boundary, you get an equation for it, and you're solving a one-dimensional absolute max-min problem on each one. And that's how you gather up all of your candidates. Okay, and I'm out of time. That's the end of this section anyway. So, okay, because of a vote, I will start 13.9 on Friday, and review for a test on Wednesday. Very well.
I didn't feel it was.